It's week 3. Okay. Good evening, everyone. Welcome to the week 3 of this course, Principles of Modern CDMA, MIMO, OFDM wireless communication system. So today we will solve few problems based on the week 3 lectures, whichever is taught in the NPTEL portal. And also this video will be recorded and will be shared in the NPTEL portal. So before starting, like we will see before starting the tutorial session, first we will see the basic understanding of multiple antenna system. So basically, multiple antenna system is used like to increase the spectral efficiency and the data rate. So as the name specify multiple antenna system, so there will be multiple antenna at the transmitter, as well as it may have multiple antenna on the receiver side as well. So let's consider a simple multiple antenna system which have only one antenna at the transmitter end, but there are multiple antenna at the receiver end. Uh, but there will be multiple antenna at the transmitter end also. That system is known as MIMO, that is multiple input multiple output. So here the transmitter antenna 1 is transmitting to receiver 1 and receiver 2. So the fading coefficient between T1 and R1, let's assume H1 and H2, and the received symbol is Y1 and Y2. So Y1 is equal to H1 X plus N1. Here X is the transmitted symbol. So we can write X is the transmitted symbol. Y is the symbol received. And here the symbol received by receiver 2, that is RX2, will be Y2. So this is given as H2X plus N2. N1 and N2 are the noise. So if it is a noise, then it is uncorrelated and the mean will be 0. So expectation of N1 N2 will be 0 because it is uncorrelated. Both the noise are independent of each other. And each has power sigma square. So power is given as so we can also write in the form of vector, like we can write vector y is equal to vector hx plus vector n. Here we can denote in the form of vector like this: y1 y2, this is our vector y, h vector is h1 h2, and n vector is n1 n2. So this is our noise vector. This is our channel vector h, and this is our received vector y. And let's suppose after combining weights of each received signal, we can write as y tilde is equal to w bar t y bar, and w bar is equal to w1 w2. And y bar we can write as h bar x plus n bar. So this is our signal component, and the second part is the noise component. So what will be the signal is to noise ratio here? So the power of the signal will be W bar T H bar mod square into P, that is the power of the symbol X, and the noise power will be expectation of W bar T N bar mod square. So this will be, so this is our SNR here. So those who have joined late, so we were discussing about the multiple antenna system, where the received symbol, we have written the received vector y1 y2 in forms of like in the vector form, like y bar is equal to h bar x plus n bar. So y bar is our received vector, h bar is the channel vector, and n bar is the noise vector. So the signal is to noise ratio. SNR value we have found for this system, which is having multiple input and one transmitter and multiple receiver antenna. And this WRTH, this is written as W1 W2, the weight vector into the channel vector. So this we will get W1 H1 plus W2 H2. So this is basically the dot product of, so this value will be maximum when the angle between them will be 0. So this theta, if theta is equal to 0, then the value will be maximum. If theta is equal to pi by 2, then value will be 0. So finally our SNR will be P into and this SNR will be maximum for value of cos square theta is equal to 0. So at theta is equal to 0, SNR will be maximum. So SNR maximum value can occur, and this value will be P by sigma square and magnitude of channel vector square. So this we can write as and if theta is equal to 0, then W bar and H bar will be aligning to each other in same direction. So W bar is proportional to H bar, and our W bar will be 1 by so this is the magnitude of the channel vector, and this is also known as maximal ratio combiner. Why this is known as maximal ratio combiner? Because it maximizes the SNR, and this occurs when the angle between W and H is 0 degree. So we'll solve some question, then we will get to know. Like we'll take one example from the classroom. So in this example, let's suppose there is a transmitter having one antenna. So this is, let's suppose, TX1, and we have a receiver array RX that have RX1, RX2. And the channel vector is given as H1 is equal to 1 by root 2 plus 1 by root 2 J. So this is a complex vector. So H2 is also given as 1 by root 2 plus 1 by root 2 J. So let's suppose we have to find SNR for this. So for finding SNR, first we will find, like we know the formula of SNR is P by sigma square and norm of H square. So we can write the equation like the received symbol. We can write in the form of vector only. Y is equal to Y bar is equal to H bar X plus N bar. So here Y1, Y2 is equal to 1 by root 2 plus 1 by root 2 J. So this is the equation what we have studied before for multiple antenna system. Now the noise power here. Let's suppose the noise power is given sigma 1 square or sigma 2 square is equal to half. So here we can directly write the value as half. Now using the maximal ratio vector, so the optimal maximal ratio vector will be, so this is just the unit vector because we are dividing the vector with its magnitude. So MRC vector is just a unit vector. So the value of the magnitude of H vector is given like this. So this will become under root of 1 by 2 plus 1 by 2 whole square plus under root of 1 by 2 plus 1 by 2 whole square. So this will become 1 plus 1. So this will become root 2. So our optimal MRC vector W bar will be H bar divided by magnitude of H vector. So it will be 1 by root 2. And our H vector is 1 by root 2 plus 1 by root 2 j. 1 by root 2 minus 1 by root 2 j. And the SNR formula, here it was W bar transpose, but for the complex vector we will take Hermitian. So what will be W bar H into H bar? So see, W vector is 1 by root 2, 1 by root 2 plus 1 by 2j. So W bar H will be W transpose conjugate. So first we will do W transpose. So this will become and there is a conjugate symbol. So for conjugate symbol, we will do change the sign of the complex term. So this will be our W bar Hermitian into vector H vector. So after calculation, we will get, so 1 by 2 like all the complex term will get cancel out when you do the multiplication and expand it. So only we will get the term which is the real part. So the final the answer will be, this will become 2 by root 2. So it will be root 2. So W bar Hermitian H vector mod squared will be 2. So our SNR value we have to find. So we have got the first term W bar Hermitian H mod square. This term we got 2. Now in the denominator sigma square we already have. The power P will be already given in the question. And we have to find norm of W vector. So this we can find as So this value will be also 1 by 2 into 2. So we'll get at a 1. If you calculate from the W1 and W2, like this is our W1 and W2. So when you do this calculation, the answer will be 1. So the final SNR value will be 2 into P divided by sigma squared noise power is given as half into 1. So it will be 4P. So this SNR value by maximal ratio combining is 4 into P. So in this way we can find. Now we will move to the question. So we'll solve the questions now. So the first question is we have to find the diversity order. So we'll write first the formula of diversity order. So as we studied in the lecture, the diversity order D is given as limit SNR tends to infinite log of half e to the power of minus half SNR divided by log of SNR. Actually, the main formula is probability of SNR. Like the actual formula is minus limit SNR tends to infinite log of probability of error divided by log of SNR. So we all know that probability of error in AWGN channel is given as half e to the power of minus half SNR. So now we will substitute this value. So our D will be minus limit SNR tends to infinite log of half minus. Actually, we can write this as the complete term as log of half plus log of e to the power of minus half SNR. We can write this because log m into n is log m plus log n divided by log SNR. Log of E will become 1, so it will become minus of half SNR divided by log of SNR. So as SNR tends to infinite, so log of half, this term will be very negligible. So this will be equal to minus half of SNR. Okay. So our value of D will be minus limit SNR tends to infinite. So it will become half of SNR divided by log SNR. So now, like we can use L hospital rule for this kind of limit equation. So we can do the derivative. So D will be half divided by 1 by SNR. So this will be limit SNR tends to infinite. So this will be half into SNR. So this value will be infinite. So option B is the correct answer for this question. Now coming to the question number 2, that is approximate. We have to find the approximate bit error rate for high SNR in a system with L is equal to 4 independently fading receive antenna. So there is L is equal to 4 here given. So we have studied a formula in the tutorial session that bit error rate is equal to 2L minus 1 CL into 2 into SNR to the power of L. So here we have to substitute the value like L is equal to 4 and we will get the answer. So we can substitute. And before that, so this is the approximate equation. This we will use in this question. For multiple antenna wireless system. Now the actual equation is a little complex, that is 1 minus lambda by 2 to the power of L summation of L is equal to 0 to L minus 1 So this is the actual equation. So in this lambda, the value of lambda is equal to SNR by 2 plus SNR. So when we do the approximation, like after you expand that formula given above, and when you do the approximation, the final equation, we get this for high SNR. So this is whenever the question it is given for high SNR, we will use the approximate equation. So now we can substitute the value of L. So bit error rate is equal to L is 4 here. So 2 into 4, 7 C4 into 1 by 2 into SNR to the power of 4. So this is equal to 7 factorial by 4 factorial into 3 factorial. So finally the answer we will get as 35. This term will become 35 divided by 16 into SNR to the power of 4. So option B is the correct answer for this question. Now let's take one more theoretical question. Using the assumption of high SNR, find bit error rate for L is equal to 2 antennas. So this is a multiple antenna system. For the signal is to noise ratio in dB is equal to 20 dB. So here SNR is given as 20 dB. So 10 log 10 of SNR is equal to 20. So the value of SNR will be 10 to the power of 2, that is 100. Now what is the formula of approximate bit error rate? That is equal to 2L minus 1 C of L 1 by 2 into SNR to the power of L. So L is 2 here. So we will substitute. So 4 minus 1, 3 C2 1 by 2 and SNR is 100. So the answer will be 3 by 4. So that is equal to 3 by 4 is 0.75 into 10 to the power of minus 4. So that will be 7.5 into 10 to the power of minus 5. So like this we can solve this kind of questions. So now coming to the third question. So it is given, consider L is equal to 3 receive antenna. So there are 3 antenna at the receiver end in the wireless system with the noise variance. The power of noise is given as minus 3 dB on each antenna. So consider the weighting vector with combining weights. So these are the weight vectors given, W1, W2 and W3. What is the approximate dB noise variance at the output of the maximal ratio combiner? So basically the noise power is given as sigma square norm of W square. So this we have studied. So this is equal to W1 square, W2 square plus W3 square. Now we have the value of W1, that is 1 by root 2 plus j by root 2. W2 is given as 1 by root 2 minus j by root 2, and W3 is given as root 2 plus j root 2. So the final value will be half plus 2 plus 2. So this will be 2 plus 4, that is equal to 6. And sigma square norm of W square will be, sigma square is given as half. It is given as 3 dB. So 10 log 10, sigma square is equal to 3. So sigma square is equal to 10 to the power of 0.3. So this value is it's even minus 3. So 10 to the power of minus 0.3. So it will be 1 by 10 to the power of 0.3. So this value will be 2. Sorry, this value will be half. Because 10 to the power of 0.3 is approximately equal to 2. So we can find like 10 log 10 sigma square is equal to minus 3. So sigma square is equal to 10 to the power of minus 0.3. So this value is equal to half. So this will become half into 6. So this is equal to 3. So now the noise power is 3. So in dB it will be 10 log 10 into 3. So it is equal to 10 log 10 into 0.477 dB. So that is equal to 4.77. So the correct answer is option number C from the given options. So now we'll move on to the next question, that is question number 4. So in this, consider a multiple receive antenna wireless channel with 12 antennas such as HI is equal to H of 2L minus I plus 1. For value of I is greater than 1 and less than equal to L. So here HI being the IID Rayleigh fading channel coefficient. So that the diversity order of this system is. So here we have to find the diversity order. So we all know that probability of error will become is 2L minus 1. So this is the probability of error for the L antenna system. So here L is like 2L antenna system is there. So probability of SNR in this question will be 2 into 12, that is equal to 4L minus 1 C2L. So this is our probability of SNR. Now we will use the diversity formula. D is equal to minus limit SNR tends to infinite log of, I think my pencil got discharged, so we will wait for 2 minutes. Just we'll wait for 1 minute and then we will start solving this question. So actually in this question we have to find the diversity order. So the diversity order formula, as we have already seen above, the formula of D is minus limit SNR tends to infinite log of probability of error divided by log of SNR. So now we know that probability of error for the L antenna system as given, but in this question it is given 2L antenna. So everywhere where L value is there, we will substitute L with 2L. So now we got the probability of error. Now we have to find diversity order, that will be minus limit SNR tends to infinite log of probability of error divided by SNR. So this formula we will use. So this will become log of sorry, here it will be 4L divided by log of SNR value.
Hello, sir.
You can write log of 4L minus 1.
Sir, that is C2L. Hello, sir.
So we can expand this equation like this. So the one term will be minus of 2L plus log of 4L minus 1 CL 1 by 2 to the power of 2L divided by log of SNR. Now when SNR tends to infinite, this value will tends to 0. So the D will be minus 12, that is equal to 2L. So for this question, the correct answer is option number B. So that will be 2L. So we'll move on to the next question. So in this question, consider a wireless channel with two receive antennas and single transmit antenna. So there is two receive antenna and single transmit antenna. Given the Rayleigh fading wireless channel coefficients for both the links are independently fading with average gain 1 by root 2, and the expectation of mod of hi like channel vector square is given as 1 by root 2. So the br is a function of snr, so that is equal to p by sigma square. P is the transmit power and sigma square is the noise power is given as. So we have to find the br as a function of snr, and snr is given p by sigma square. So for this kind of question, like we have already studied, snr is given as p by sigma square, and effective snr, that will be equal to 1 by root 2 of snr because of the this channel coefficient, because due to this channel like fading coefficient, it will be multiplied with 1 by root 2. So the bit error rate for L is equal to 2 antenna. So here we have seen the formula. So that is 2L minus 1 CL 1 by 2 of SNR to the power of L. So L is equal to 2, so it will be 3C2 1 by 2 into SNR to the power of L. L is 2. So it's equal to 3 into 1 by 4 into 1 by SNR squared, and this will take the SNR effective because there is a channel fading coefficient here. So it is equal to 3 by 4, and SNR effective is 1 by root 2 of SNR. So that is equal to 1 by 2 of SNR squared. So that is equal to, sorry, SNR effective is 1 by root 2. So this 2 will go in the numerator. So it is equal to 3 by 2 of SNR squared. So the option D is the correct answer for this question. Now moving on to the question number 6. Consider a wireless system with L is equal to 4 antennas and the channel coefficient given as H1 is equal to 2 plus J, H2 is equal to minus 1 plus 2J, H3 is equal to minus 2 minus J, and H4 is equal to 1 minus 2J. Let the noise variance is equal to half and transmit power P is equal to 3 dB. So the SNR at the output of the maximal ratio combining is approximately, so SNR due to maximal ratio combining is this is the formula. So here so this is our H value and power is given as 3 dB. So 10 log 10 power is equal to 3 dB. So P is equal to 10 to the power of 0.3. So this value is 2 into 2. So this will become 4 into 5, 6, 10, 14, 15, 20. That is equal to 80. So now when we find in terms of dB, so it will be 10 log 10, 80. So this 10 into log 10 of 80 is around 1.9. So this is equal to 19 dB. So option C is the correct answer for this question. Now moving on to the question number 7th. That is the gain G is given for the maximal ratio combiner where H is the channel vector in a multiple receive antenna wireless system with independently identically distributed relay fading coefficient for L is equal to 4. So we all know that the probability density function for this FGG is given as Z to the power of L minus 1 by L minus 1 factorial into E to the power of minus G. So this can be given as here L is equal to 4. So the value FGG is equal to G to the power of 3 divided by 3 factorial e to the power of minus G. So this will become 1 by 6 G cube e to the power of minus G. So the correct answer is option D. Now if the BR of communication system decreases as 1 by SNR cube plus 1 by SNR to the power of 4 at high SNR, the term 1 by SNR to the power 3 is dominates. However, the diversity order is, like in this question we have to find the diversity order. So we all know, so like the BR of system decreases, like it is directly proportional to this term. Okay, so whenever like SNR is very high, so SNR to the power of 4 will be much greater than SNR to the power of 3. So this term is negligible to 0. So we can take it as like this. So it is depending on SNR to the power of 3. That is the dominating term. So here the diversity order of the system is 3, because 1 by SNR to the power 4 will be very less. Like both may be equal to 0, but 1 by SNR to the power of 4 is much lesser than 1 by SNR to the power of 3. So this is the dominating factor here. So move on to the question number 9th. Consider an L antenna wireless fading channel where HI is the fading coefficient and YI is the received symbol on the antenna I. So let phi I denotes the phase of HI, the output of the equal gain combiner is. So the output of the equal gain combiner, the equation is I is equal to 1 to L e to the power of minus j phi I into yi. So option B is the correct answer for this question. Now moving to the last question of this today's lecture. What is the approximate SNR to achieve bit error rate of 3 by 4 into 10 to the power of minus 12 for a wireless system with L is equal to 2 receive antenna and maximum ratio combining is used. So for 2 received antenna, we know the formula is 2L minus CL 1 by 2 to the power of SNR to the power of L. So L is equal to 2, so it will be 3C2 1 by, and this value is given as 3 by 4 into 10 to the power of minus 12. So we have to find the SNR. So 1 by 4 into SNR square into 3, that is equal to 3 by 4 into 10 to the power of minus 12. So SNR square is equal to, this is imply that SNR is equal to 10 to the power of 6, because SNR square is equal to 10 to the power of 12. So now we have to find in dB. So SNR in dB is equal to 10 log 10 to the power of 6. So that is equal to 60 into 1 dB. So that is equal to 60 dB. So option C is the correct answer for this question. So we'll stop the lecture here only today. And we'll have next lecture on Saturday, that is 3 to 5 p.m. So these are some of the questions which we solved based on the concepts taught in the week 3 of this course. And this video is recorded and will be uploaded on the YouTube as well, and the link will be shared in the NPTEL portal. Thank you everyone for attending today's lecture. So I will close the lecture now, and we'll meet on Saturday 3 to 5. Thank you.